guys. So this is from worksheet 2, week 5. So week 5, worksheet number 2. So this solution is a very lovely, like in-depth solution. So I actually just kind of want to scroll through it here and point some very important things out. So, okay, I'll pause and let you read the problem statement, and then we'll pick up. Okay. So, all right, so we have a motorcycle, and it's basically just driving around this like loop-the-loop here, okay? So this guy is driving all the way around in a circle. So we're trying to determine the normal and frictional forces at the 4 points. And then determine the minimum coefficient of static friction needed to complete the stunt as planned. So basically what we're going to do is solve for the coefficient, like solve for what static friction is needed to prevent the motorcycle from slipping at each point on the circle. And then whichever one is the largest is going to be like, that's like the minimum friction that we need, right? Because at the point that requires the most friction, if you can't get that friction, you can't complete the stunt, right? So the minimum is going to be the point that requires like the most friction. So like that would be our limit, right? We'd have to have at least that much to pull it off. Okay. All right. So, okay, let's kind of scroll through what's going on. I want to point out one thing about static friction when it comes to wheels. So wheels are confusing often because you think about them moving, right? So it really doesn't matter that they're moving. If we think about the surface as it's rolling, if each point of contact maintains this like nice normal force and there's no slipping, between the wheel and the surface, we're good, right? We can say that our static frictional force works out very nicely. So that would be slipping in one case. There's also like where you're looking at the wheel head on and it could kind of slip side to side. So if we want to complete the stunt, we need to make sure that the wheel doesn't spin out this way and the wheel doesn't kind of spin out this way. In this case, though, we're more concerned with the first case. Okay, so this is going to be weird, but when you're thinking about the motorcycle, almost think about it as just like a block. Like, and if that block were to slide down, what is the friction direction that would prevent it from sliding, right? Because as those wheels are spinning, okay, as they're spinning, we're assuming that like it maintains a nice like normal force at each point as the wheel makes contact, okay, and that it's not going to slip on the surface. So we don't want the wheels to spin out. We want it to make contact on each surface, right? But if the wheels kind of skid, then we have a problem. So the static frictional force would be kind of opposing the direction it would slip back. Now, one really weird thing is that actually at the top and at the bottom, the static friction force is going to be equal to 0. And the reason why is because like I wouldn't have any, I don't have any force that I need to oppose, right, to keep it from slipping. On these sides here, if I do my free body diagram, okay, think about the fact that I have weight here, right? I have a normal force coming straight out because it's going to be perpendicular to this surface always. Here, the weight would just be going straight down, and the normal force would be coming out perpendicular to the surface, right? Or if I think about if I draw the normal force down here, right? Same thing, I'm just sort of moving it up through the center of gravity. Okay, and then same thing here. The normal force and the weight, this is, I know, very bizarre, but they're pointing in the same direction. And here I have the weight and then the normal force going up here on Fs. I wouldn't need any friction here. Okay, so cool. So now let's kind of look at the solution here. Okay, so you can go ahead and read through this part. I'm just kind of look at the pieces. So first condition, right, we're at the bottom here. Okay, we're going to use the sum of forces is equal to mass times acceleration. Okay, and we have the normal force pointing up, right, minus mg. So this is sum of forces in the y direction is equal to the normal force pointing up minus the weight going down. And then one thing about the centripetal acceleration, I'll say Here, remember at every single point that centripetal acceleration is always pointing along the radial direction and towards the center of the circle, right? Always towards the center of the circle, always along the direction of the radius at every point, okay? So it's no exception for this first piece, okay? So our centripetal acceleration would be pointing in this way. So we basically are setting this equal to, right, m times AC, and this AC is equal to v squared over r, okay? So we are plugging in v squared over r here, right, on this side for our MAC. Okay, for our sum of forces in the y. So MAC in the positive direction pointing out. So then if we simplify things a little bit over here, we get our normal force, okay? So we solve for the normal force like it asked us to. And we note that friction is not necessary because there's no horizontal acceleration. So friction is what's going to counteract that horizontal acceleration, but we don't really have anything going on here, right? So it's like some forces in the y, it's just 0. We don't have anything that we need to balance here. So no friction necessary on the bottom, okay? That wheel is just gonna roll at each point, and we are okay. It's not gonna accelerate. Okay, so then the normal force for this guy, if we look at this, it's going to point up. The weight's going to point down. And remember, the friction, if we just sort of think about it as a block, that would be sliding down. The friction's going to be pointing up. So we set up things as sum of forces in our separate directions here. So sum of forces, we're doing it along the direction of the normal force here. So sum of forces, let's say maybe in the x direction. Be equal to the normal force pointing in, and that's going to be equal to MAC, and this just v squared over r is MAC. Okay, so then if you plug in everything here to just kind of solve for that normal force, this is what this would be equal to for this point here. Okay, so then next we're doing basically sum of forces in the y direction. It's going to be equal to the, sum of forces in the y is equal to the frictional force minus the weight, which is equal to 0. Because we're not accelerating, up. We do have, we want these forces to be balanced, and moving with constant velocity, right, is not the same as acceleration. If the velocity is constant, the acceleration is 0. So he's moving forward, right, with this constant velocity, but there's the forward acceleration is still 0. Okay, so we can do this piece here, and we solve for our frictional force for this. So this is a pretty high frictional force here. Okay, so yeah, so that's for part 2. Then for part 3, we're looking at this figure here. So that's what it's answering. So case 3. Okay, case 3 here. Oops, sorry. We're upside down. They're pointing in the same direction. So we're basically just looking at sum of forces in the y direction. And it's going to be equal to mass times the centripetal acceleration, right? Because remember, AC is always pointing along the radial line and towards the center. No exception here. Okay, so they just rearranged this equation here to solve for the normal force as the problem asked. And then once again, friction isn't necessarily necessary since the motorcycle isn't accelerating horizontally. So there's no frictional force required to balance a horizontal force. Okay, so not necessarily required to pull off this stunt. Okay, so all right, then the last part, this guy here, we have the normal force here, the weight going down, and we have friction. Again, if you could just kind of think about it as like a block, if I put a block here, like what direction would it slide down? So that's what we're trying to prevent, okay? So we would require friction if we think it's gonna like slide away. So we would have like a piece of the weight essentially pointing in that direction, which is why we need that friction to oppose it. Okay, so for this problem, for the first step, what they're doing here is sum of forces in this direction here. And the angle is a little bit tricky for this one. I think they give you, so 45 degrees past the top. So if we think about what that means for how we set up our angle, so 45 degrees past the top, if this is our, if we think about like the top angle, VCAR is, the angle between the normal and the weight is just 45 degrees here. Let me take a second to think on that one. I might include this as a footnote here. But let me just kind of take a look at what they did for their angle. G cosine of 45. Yeah. So because it's tilted, so this ends up being 45 degrees. 45 degrees past the top. 45. I'll take a second. I'll post an addendum footnote here. I don't want to get kind of too lost in the weeds here. Okay. So we're setting up this equation here. This is going to be sum of forces in the x direction is going to be equal to, so we're just setting this to be our x, positive x pointing in. And then for the y direction, we're going to set that equal to the frictional force here, right? So this is going to be in the positive y hat direction, okay? So sum of forces, y is equal to, sorry, sum of forces in the y is equal to the frictional force minus w sine of theta, which equals 0, okay? Which is, yeah, minus w sine of theta, so minus mg sine of theta, right, is equal to 0. And then this is just rearranged down here for the same solution here. So doing sum of forces along the y direction and then along the x. So plugging that in, solving for the frictional force that you would need to pull off that. And then, yeah, there's also a little trick kind of at the end to how to solve it a little bit easier. But I kind of think all of the steps were actually very useful to kind of point out some overall considerations. So the last piece of the question, if we scroll up, sorry if I'm giving you guys whiplash here. So the last piece of the question is the minimum coefficient of static friction needed. So we found the weight of the object. The normal force. So for each point you found the normal force, right? And then the frictional force, so normal force, and then the frictional force, right, for each point, normal force, and the frictional force for each point. So we know that the frictional force, right, is equal to the mu sub k times the normal force. So in order to find the, mu s. In order to find the static friction coefficient, right, it would be the frictional force that you found divided by n would be equal to the minimum mu sub s, okay? So when we say minimum, we need to find the largest mu sub s value to pull off the stunt. And so in that case, it's actually going to be equal to the side case here. So, blah, blah, blah. So it's going to be this guy here. I think our final answer, I'll let you guys kind of scroll through this one on your own. I don't want to get like too intense here. So this is the minimum here. So it's going to be these two. So you would actually just solve for it at each case. But notice it's actually going to be the one where it's on the side. So that should make sense, right? Like this is where we're going to need the most friction to get up that wall, right? So conceptually, I think that should add up. So I'm sorry this is incredibly long. Feel free to go through this one. If you have questions, let me know. Hopefully the explanation is pretty straightforward, but let me know if it is not. So hopefully after this, it kind of makes sense how to model a free body diagram, no matter where up in the air this object kind of is.